Let's start out by looking at what it shows do this week in Buzz, like we basically do every week, right? All right, so go into Buzz, looking at our Foundations of Programming class here in Buzz. If we go to our grade screen, see that last week the Module 4 project was due. That was due yesterday. So hopefully you've got all this in. 3 of these were 100-point assignments. So hopefully you got all those in and have done well on those. If you got them in, I've gotten most of them graded. I don't have all of them graded. So if it shows that it's still waiting to be graded, I'll get to it this week here. But today, see, February 26th is this coming weekend. So we are working on number systems. We're going to be doing number systems today. So let's take a look at number systems. We're done with Module 4. We're for Module 5, the number systems lesson. So let me just start with, let's just start about talking about number systems first. So we use the decimal system, right? And that's base 10, decimal. Base 10. And so all of our numbers go from 0 to 9. We don't include 10, right? We go from 0 to 9. And if we have a big number, 0, 0, 1, 1, 7, 0, 0, this is the tens place, right? Anything less than 10, we put a number in there. And then we get to here. This is the 100. I'm sorry. This is the ones place. That's the tens place. Gosh, like I've never used the decimal. The ones place. Anything less than 10 would be in there. That are just single digits. Anything 10 and above it there. Then we get to the 100s. And we get to the 1000s. The 10,000s. And you're like, why are we doing this? We've known this since elementary school. Well, yes, but we're going to use some other number systems today. So up to the millions place. If we have a number here, that means it starts with 1 million or 2 million or 5 million or whatever it is. Anything less than 10, because we hit 10, we jump to the next digit. So today we're going to talk about binary, because computer uses binary. And binary is base 2. So when you have these numbers, this is again is the ones, anything less than 2. If you have a 2, that moves up to this one. Just like if you have 10, you jump over to this one. 2 jumps over to this one. And then this one would be 4. And this would be 8, 16, 32, and 64. Notice it's powers of 2. Like this is powers of 10. Since we use a base 10 system, 1, 10, 100, 1,000, 10,000. It's all multiplying by 10. This is all multiplying by 2s. It's the same concept, multiplying by 10s or by 2s. So if we want to write, let's see what number this is. Yeah, this is 11,700. We recognize that, but what number is this? It's not 11,000 because this is not base 10. So this is a 16 plus an 8. And there's no other numbers. So this is the number 24 in binary. 110000 is the number 24 in binary because there's 1, 16, and 1, 8 and no other numbers. Up here, there's 1, 10,000, there's 1, 1,000, and there's 7 100s and no other numbers. So it's 11,700 because we just add those together. 10,000 plus 1,000 plus there's 700s. So that's how we get the 11,700. You just don't think about it because it's automatic. You've been using this your whole life. It's automatic. This we have to think about. We have something in the 16s space and something in the 8 space. We're also going to learn about hexadecimal. Like hexa what? Hexadecimal. And it is base 16. Right? You'll never have a 2 in this. It's base 2. It's like you never have a 10 in this. You just have 0 through 9 in each, just zeros and ones in base 2. Base 16, we actually have 0 through 15, but we don't write it as a 15 because that's a decimal number. So I'll show you how to do this. So starting down here with the 1, then the numbers that we can put in the ones column, because if you put a number here, this is 16. And if you put it, the next one is 256. And all of these go by 16, multiply by 16 to get bigger and bigger, which I'd have to grab my calculator to know what the next one is. But in this first space, we can put anywhere from 0 to 15, but you have to write it like this. 0, 1, this is how you count in hexadecimal. 3, 4, 5, 6, 7, 8, 9. So far it looks pretty similar to the decimal system, right? But when we hit the 10, it's A, B, C, D, E, F. This is 10, this is 11, this is 12, this is 13, this is 14, this is 15. That's as far as we go. We don't go past F, because if we have something bigger than F, then we move over here and put a 1, because we have 116. So this one equals 16 because we just have 1 in the 16th place. If we had this as a hexadecimal number, 1C, what does that equal? Well, there's a 1 in the 16th place, and there's a C, which is 12. So that's the number 28. 1C. So we're going to look at both of these other number systems in addition to decimal today. And then we'll have a 5-question assignment on that. But you need to pay attention, because that means next week we'll be writing a program using it, right? That's what we always do. It just seems to always do that. So let's go back and look. Types of numbers. How many teaspoons are in a mile? Like, what? What about your height in gallons? How many gallons tall are you? That's not typically how we would measure distance or height, but you can probably figure out a way to somehow convert that. I'm 9 gallons tall. I don't know. In programming, there's a few different types of numbers, and some are used to represent symbols. Some in calculations present colors or memory locations. So we're going to learn about the different number systems and how they're used to present. So number systems. Our world runs on 2 things: language and mathematics, right? Language and mathematics is pretty much, that's why you have to take 4 years of math and English, because that's what our world runs on. So we use language to communicate, and we math to pretty much do everything else. So think about it. If you're an architect, you need words to describe what you're doing. You need numbers to make it work. If you're a musician, words come in handy for lyrics, but the numbers arrange the music and set the tempo. In programming, the type of number used depends on the type of data. Each number system has a different base, which is a different number of digits it uses. So the decimal number system is base 10, so it uses the digits 0 through 9. So let's look at some of these others. So decimal system base 10, we're very familiar with that. 0 to 9, like money uses the decimal system. All the amounts use numbers based on the 10-digit system, like $1.50. Then we have the binary system that I just showed you on paper. Binary numbers are what computer languages are made of. They are based on the digits 0 and 1. So the combination of zeros and ones can be converted into other types of numbers or even words. You can use the binary system to write other types of numbers or words. So here it is, the binary for the decimal 123. This right here just tells the computer it's a binary number. So this is the number 1, the number 2, and the number 3. These are placeholders. So just look at these last 4. Look at these last 4. That's a 1. That's a 2. That's a 3, because there's 1 in the 2 spot and 1 in the 1 spot. Hexadecimal numbers are the most common in the computer world. They're used for like colors and memory locations. So sometimes if you look at code on something, you'll see color, and it'll have like a A6F201, and you're like, what? That's hexadecimal, telling the computer what color. So it uses 0 to 9 and A through F. So all colors have a hexadecimal code. Like here's hashtag FFD700 is the hexadecimal code for the color gold. And we can figure out in hexadecimal what number that is, but we got the zero. I see there's a 256. That's seven times 256. So that's a big number. And then we go up to the bigger ones over there. Let's go over here. Things aren't always O and F. There are two types of people in the world: those who understand binary and those who don't. Right? This is a 1, that's a 2. So that's a 2 in binary. There are two types of people in the world: those who understand binary, those who don't. So the great thing is we can convert from one number to another. If you got it in decimal form and you need to use it in binary, you can do that. Right? We got the 0 place, the 1 place, the 2 place, the 4 place, the 8 place. We can put them in wherever we need to. So in decimals, we know everything is a power of 10. 1 is 10 to the 0 power, 10 is 10 to the first power, 100 is 10 to the second power, 1000 is 10 to the third power. It continues on. 0, the ones column, see, they're just talking about that. And so on. Same's true for binary. So one easy way to convert, use an online calculator, but actually Python will convert for you as well. So we'll talk about that. So here it is. If you want to go from binary to decimal, you could draw on your fingers with a marker. And here's a quick, easy way to do it. Hold up your non-writing hand, right? Whether you're left-handed or right-handed. Start with the leftmost finger and write 16 on it, which if it's your left hand, you're going to do your thumb. Your thumb would be the 16. 8, 4, 2, and 1. One number per finger. So these are powers of 2 because we're going to convert to binary. So think of each individual finger as a binary number. When a finger is raised, it represents a 1. When it's down, it represents a 0. So if you close your fist, that's a 0. If you lift all your fingers, that's a 1, 1, 1, 1, 1. And you add all them up, and you get 31. You got 16 plus 8 is 24, plus 8 is 28, plus 2 is 30, plus 1 is 31. So all 5 fingers up is a 31. So here is numbers down here. There's the 31. This one would be 24, 28, 30. That's 30. This is just 6 there in the middle. It's just a 4 and a 2. Everything else is a 0. So that'd be 0, 0, 1, 1, 0 is 6. There's how you get the number 3, just the 2 and the 1 are the number 1. So can you come up with the binary number for 12? Well, the binary number for 12 would be the 8 and the 4, right? Hold up the finger with the number 8 and the number 4, and you're holding up 12 because 8 plus 4 is 12. So that would be 0, 1, 1, 0, 0 because you don't need the 16, you don't need the 2 and the 1, you only need the 8 and the 4. That's the binary number for 12. All right, let's look over here. Binary to hexadecimal. The hexadecimal system is 0 to 9, A through F, like I was showing you. It makes it ideal to represent a binary number with fewer digits. So binary takes a lot of characters, a lot of digits. And each one's considered a bit, which is the smallest storage in your computer. And 4 bits represent one hexadecimal number. So you can shorten things down. So if we have in binary 11000111, that takes up 8 bits of storage in your computer. Now, storage is a lot cheaper than it used to be. When they first came out with computers, it cost you a lot of money for a little bit of storage. And so you would want to try to convert numbers like this. They wouldn't use the binary. If they could, they'd put it in hexadecimal because it only takes 2 bits of information. See, this first one right here, 1100, is 12 in decimal. And then over here, this is 0111, that's 7. So instead, we can write a 12 with a C, because remember, after 9, it's A, B, C, 10, 11, 12. C is 12. And then 7, we just write as a 7, because we can go anywhere from 0 to 15 or 0 to F in hexadecimal. So it's very shorter. So the good news is hexadecimal numbers are much shorter than binary numbers. Even if we were writing these two numbers in decimal, it'd be 12 and 7. That would take 3 bits of information. So hexadecimal is shorter than decimal. So let's look at the binary and hexadecimal numbers for the value 15. So which would you rather type out, right? So this is 15, 1111. That's a 1, a 2, a 4, and an 8. Hexadecimal, it's just an F. Easier, simpler. we just don't commonly think in binary or hexadecimal, so it takes a little work at first. So let's compare the number systems. Here's all three: hexadecimal, binary, and decimal. So let's look at all. Let's look at number 5. 5 is 0, 1, 0, 1, or just a 5. If we look at 13, it's 1, 1, 0, 1, or just a D. 14, 1, 1, 1, 0, or an E. So there is a chart with the first 16 numbers in both systems, starting with 0 in decimal. 0 to 15, that's 16 numbers. Let's look over here. So I'm going to have some converting in Python. So this is nice. You can do this. Python can save the day if you're trying to convert this. So you can put age equals 17. That's a decimal number, right? That's the numbers we're used to, 17. And then we could say, okay, we're going to take binary age as a variable name, and we're going to make it equal to the binary of age. So it says take this decimal number and convert it to a binary and save it here, and then just print that. So it will print it in binary. So let's look down at this program they have. So if we read over the code, number systems, define main, we start our main function, assign a decimal number to D. Okay, that's a comment. So we assign the number 7 to D, and we print that. The decimal value is string D. So we're going to print what that number is. And then this portion of code will convert that to a binary number. So we're going to say the B is the binary of whatever the decimal number is. So print that. The binary value is B, main. And notice we don't have to convert that to a string because it's in binary, which computer already likes. Let's run the program and see what it looks like. Okay. The decimal value is 7. The binary value is 0B111. Now, let me tell you why it did it that way. This is a code, 0B, to let you know I'm printing a binary number. So when you look at a number on there, if we didn't have that and it just had the 111, is it printing 111? Because it could print decimal numbers. And it says, no, since you see the 0B in front of it, this tells you I'm printing a binary number. So that's an important thing to recognize, that Python will notice that. So let's change the value of D. Let's say instead of 7, let's make it 142. How about that? Let's run that. Oh, 142 in binary is 100011110. So if we make it 143, it should just change that last one to add 1, right? Just adds 1. Yep, just adds 1 down there. Let's make it a really big number, like 652,138. How about that? Woo! 1001111100110. That's a long binary number, but it'll convert it and print it for you real easily. Let's look at the next example. Okay, I'll raise this up. Number systems, define main, assign decimal number D, so it's back to 7. Convert it to a binary number. Print the binary value is this, and now convert a binary number to a decimal. So gives us the format, integer, number, and the base. So the integer is B because B is a binary number, and we want to do base 2. So the decimal value is string. Let's see. So the binary value is 1111. The decimal value is 7. So it says converting a binary string back to a decimal can be done with the integer function. Say we told it make it an integer again, back to an integer. This time 2 parameters needed. The first is the binary string. The second lets Python know that the number is base 2. So when we put the number in there, we have to tell it what is this number based on. Is that a decimal number I'm entering? Is that a hexadecimal number? No, I put 2 to let it know, oh, that's a binary number that I'm telling you. Convert it to an integer. Because binary is base 2. So I have to tell it what base I'm using. So let's change this again. Let's go 705 instead. And program in binary, it's 1011000001. The decimal value is 705. Again, we told it it's a base 2 number, and it'll convert it. Let's look at the next example. Okay, assign a decimal number to D. This time we're taking 156, and we're going to convert that to a hexadecimal number. So H equals hex. There's the command to convert it to a hex. Hex, whatever the value of D is, which we know is 156, convert it to a hexadecimal number, and then print what it is in hexadecimal. And then this, we can convert it back to a decimal. Using that integer again, take H, which is the hexadecimal number. We tell it that's a base 16 number, and they'll say, okay, so it's base 16. I can convert it back to a decimal now that I know. And then, of course, in main down there. So let's run the program. Decimal phase 156, converts it to hexadecimal, and this uses a 0x. It was a 0b when it's printing a binary number. It uses 0x for a hexadecimal number to let you know, hey, this 9c, that's not 9c, that's hexadecimal for 156. And then it converted it back to a decimal again. We print it back as a decimal. So 0x tells you it's a hexadecimal. 0b tells you it's a binary. And if there's nothing out in front of that, you know it's decimal, 156. It says assign new values to D. Observe the output. All right, let's go up here and say, okay, let's put a 5 on the end. That's 1,565. Let's see what that is in hexadecimal. 61D. 61D. Again, you can change whatever. If you just want to say the number is 16, 10. 1 in the 16 spot, 0 in the ones. 17 would be one more than that, right? 1 1. So 1 1 in hexadecimal is 17, 1 1 in binary is 3, 1 1 in decimal is 11. Let's look at the next example. All right, define main, user input. Now they're having the user input b equals 0b plus input, enter a binary number. So we have to attach this to the binary number so the computer will recognize it as a binary. Print your binary number is this, and then they'll convert it. Whatever b is, which remember we're adding the 0b in the front, convert it to an integer, and then print what the decimal number is. So if we have a binary number and we don't know what the decimal equivalent is, this programmer is written to help that. So run program. I've got a binary number. I don't know what it is. I know it's a 1101011011. What is that as a decimal number? I have no idea. All I know is the binary number that I have. So I can run this program, and they'll say, "Oh, that's 859." You gotta add this to the front of it. See, it's taking this variable, adding the 0b plus all them ones and zeros I just entered. So then when it converts it, we tell it, take that number, and it's base 2, and print what it is in decimal. Got to use only ones and zeros. Okay, our last example, define main, print table headings. Print, here's a number systems chart. So it's printing the decimal, the binary, and the hexadecimal, and it's using a loop. Okay, so this goes for D in range 0 to 16, right? Which means it'll stop at 16 and won't print that. This is a for loop. So B equals the binary of D, because D is going to be a decimal number. It's going to be an integer. So it's converting what's the binary equivalent and what is the hexadecimal equivalent. And then this loop is going to print each of those. First, it prints the decimal, and then it prints the binary, and then it prints the hexadecimal. And it's already printed these 3 column headings. So this is just a program that'll give you 0 to 16, or 0 to 15, actually. The first 16 numbers of the decimal, binary, and hexadecimal. So let's run that. Oh, there's our output. Number systems chart, which we told it to print right up here. There's your column headings, decimal, binary, hexadecimal. They put a little space in front of it just to move this over. All right, a little space in front of it. And they put another space in between just to spread these numbers out underneath the proper headings. So decimal is 0, the binary is 0, and the hexadecimal is 0. Number 0b tells us this is binary numbers. 0x tells us this is hexadecimal numbers. 1 is the same. 1, 1. But once you get to 2, it gets a little different. 2 is 1 0 in binary, but it's just a 2 in hexadecimal. And if you watch this, see the binary is going to have the 1s and the 0s added. Hexadecimal is going to be the same as decimal all the way through number 9, right? 9 is the same in hexadecimal. But when we get to 10, that is an A, right? Because we know it goes 0 through 9, then A, B, C, D, E, F. So F is equivalent to 15, which in binary is 1111. So that's just a nice example there. There's some good examples of how to use Python with binary numbers, decimal numbers, hexadecimal numbers. So after this, says do your assignment. Make sure you complete reading the lesson, practice using Python, go back and change that program I was just looking at, go back and play with that. And then do the number systems quiz, which would be the next thing here. You start that. It asks you 5 questions about the binary and decimal and hexadecimal functions. All right, so there you go. All right, any questions on that? Playing with different number systems with Python. It's very nice that Python can convert all that for you, because if you're doing something and you need to know the binary equivalent of the 1041, that takes a little math, but Python can just print that out for you. No, here's what 1041 is. Boom, 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 boom. So, all right. Get that. If you're still writing programs from the previous module, get those done, because we're going to be in this for a few weeks. But once we get to the end of this unit, last unit, no more late work accepted. So if you miss anything, or if you need to go back and redo something from the last module, you can still do that as well. As if you got a poor grade on something, you might want to go back, look at it, and redo it. So that's fine too. So, all right. If there's no questions, I'll let you guys go enjoy your week and enjoy your hexadecimals. Fun. We'll see ya.